So picking right up where we left off, we were finding antiderivatives. And what seemed like witchcraft to begin with, y'all were like spewing out these answers that I didn't realize where they came from. We decided that, hey, the power rule for derivatives in reverse does a real nice job of finding antiderivatives of things of the form a times x to the n. So remember, the process was to add 1 to get your new exponent, and then divide by or multiply by the reciprocal of that new exponent. And then, of course, you finish it off with a plus c. Very good. All right, so now here's the definition. A differential equation is simply an equation that has a derivative in it. Okay, so like if you looked at example 2, we had g prime of x equals some expression of x. By that definition, this was a differential equation, or diff-EQ as it's known. Now, solving differential equations is of paramount importance. So what does it mean to solve a differential equation? It means essentially to get back to the original function from which the derivative came. So in this case, since it was a first derivative, we actually call it a first order differential equation. Finding its solution then means getting back to g of x. You're going to go back one antiderivative. If you have g double prime equals some expression, that would be a second order differential equation, and solving it means getting all the way back to g. So you're going to have to anti-differentiate twice. So on and so forth, right? A g triple prime would be a third order differential equation. Solving it means getting back to g. All right, so now there's two different types of solution, and kind of what I mentioned the other day. If it has the plus c in it, we call that the general solution, like we call the other thing the general antiderivative. If we are given an initial information about the function, then we have enough information to find the value of c, and that is called a particular solution. But because when you take the derivative, you lose information, you lose the constant, if you're expected to find a particular solution to any differential equation, you have to have at least some information about the original function. So really now, solving a differential equation is the same process as anti-differentiation. They're one and the same. It's just a slightly different presentation style. So here's example 3. It says to solve the differential equation. And we're given f prime of x equals 3x squared plus 1. So without even them saying, how would you know that's the differential equation? There's an f prime, right? And, of course, an equal sign. It's a differential equation. You are going to be expected to solve differential equations. Now, it says here to find both the general solution and the particular solution. So notice this little piece of information right here. It says if f of 2 equals negative 3. That is what we call an initial condition. And in this case, we don't say initial corresponding to the x value given. We say initial corresponding to the original function, which in this case would be the function f. It is an ordered pair that satisfies the initial function or the original function f of x. So here's what we do. We find the general solution first. Even if you're just after the particular solution, you have to find the general solution first. And then to find the particular solution, you're going to plug in and solve for c. You're going to be able to get the value of c. And then, of course, you're going to rewrite it with that new c value. So I'll show you what I mean here. First things first, we got f prime of x equals 3x squared plus 1. We're going to take the antiderivative now of both sides. What would be the antiderivative of little f prime? Little f, right. Remember, notationally, if it has a prime, you take 1 away every time you anti-differentiate. If it started as little f, then we go backwards to big F. All right, so now we have two terms. We can use the power rule in reverse. What would be the antiderivative of 3x squared? X cubed. So here's how you could do it in your head. You start with 2, you add 1 to 2 to get 3, your new exponent, and then you multiply by the reciprocal of 3, which is a third. So a third from the power rule times the 3 that's originally there is 1. So you can do that in your head. I'm fine with you doing that. Plus, what would be the antiderivative of 1? X. Good. And then we finish it off with plus c. Good. So this is what we call the general solution, because x cubed plus x plus c is the general antiderivative. So now we'll use the initial condition. At the point 2 comma negative 3. You can say it like that. Remember, you always have to narrate what you're doing, showing what you're doing. In this case, if you want to write it as an ordered pair, that works. Or you could say 4f of 2 equals negative 3. Either one of those signal your intent. Tells people what you're doing. And now you just plug in a 2 for x and a negative 3 for f of x. You get negative 3 equals x cubed, oops, sorry, I need to plug in my 2, don't I? 2 cubed plus 2 plus c. And now it's just a matter of solving for c. So you're going to get a negative 3 on the left. That gives you an a plus 2, which is 10, which if you bring it across becomes negative, and c equals negative 13. Yeah. Colon, yeah, that's fine. Yeah. Yeah. Okay, so are we done? If we box this up, are we done? No, you did it right. You got to actually write it out. And so again, my favorite transitional word is so instead of therefore or thus. So the particular solution is f of x equals x cubed plus x minus 13. And we call it a particular solution because it is the only function now in the whole wide world whose derivative is 3x squared plus 1 that passes through the point 2, negative 3. It's very particular. It's a one of a kind. Okay, pretty easy stuff, right? Good. It gets more fun, I promise. Example 4, same thing. Find the particular solution to the following differential equation. So we know this is a differential equation because now instead of f prime, it's dy dx. We're going to look at a stricter notational burden later on when we study separable differential equations later on exclusively. But right now, this is just a first order differential equation because we have a first derivative. So our goal is to get back to y equals. So take inventory. You got a term here and a term here. Are they both written in ready to anti-differentiate format? Kinda, right? You could acknowledge it. This second term though looks kind of funky, kind of intimidating. Can I expand it or distribute the negative 1 at all to get? No. Remember, we don't have really much at our disposal except the power rule, and then everything else is just recognizing something as the derivative of something else. Wait, what? Okay, yeah, so let's go ahead and rewrite it a little bit. If the only tool you have is a hammer and maybe, I don't know, what else would you have? A pickaxe. There you go. You got a pickaxe and a hammer. You have two tools. The hammer being the power rule and the pickaxe being all the other things that you recognize the derivative of. You have to start making everything look like a nail or a rock that you would take a pickaxe to. Good. Hard labor in Siberia. So I'm going to call this 20 times 1 plus x squared to the negative first is 1 over 1 plus x squared. And now you're like, I see that. So even if the 20 were in the numerator, 20 over 1 plus x squared, you could still kick it off to the side. Now I think we've got both of them ready to go. So notice that is still dy dx equals. Now the antiderivative of the left is just y. We got two terms. What's the antiderivative of e to the x? E to the x, right? His own grandpa. Plus 20 goes along for the ride. That's your rider. If he's there in the beginning, he's there in the end. Times the antiderivative of 1 over 1 plus x squared, which of course is inverse tangent. Good. Or arctangent. We recognize that as the derivative of arc or inverse tangent. And then, of course, we trim it off with plus c. So this is called, again, the what solution? The general solution. So now to find the particular solution, y of 0 equals negative 2. So this is kind of what Lucy said. You could just say y of 0 equals negative 2. Again, that communicates what you're doing. That's your initial condition. Now this one happens to also be x equals 0, but remember that's not what makes it initial. It satisfies the initial equation, which we have above. So we get negative 2 equals e to the 0, which is 1, plus 20 times inverse tangent of 0 plus c. What is inverse tangent of 0? The way you solve that, remember, is you say tangent of what angle gives you a ratio of 0. And if you're in doubt as to which quadrant to be in, always be in quadrant 1. Where is tangent equal to 0? At 0. Yeah, tangent of 0 is 0. So inverse tangent of 0 is also 0. Plus c, and that means then that term is gone. We bring the 1 across, and we get c equals negative 3. So the particular solution is y equals e to the x plus 20 inverse, or I'll write it as arctangent this time, and then minus 3. There is your particular solution. Step by step, inch by inch. All right. So when we're asked to take the derivative of an expression, we have the verb format, right? If you see ddx in front of an expression, you know what to do at this point. It means to find the derivative of what follows with respect to x. Right now, we haven't seen a verb version for the antiderivative. We have been asked to either find the antiderivative or to solve a differential equation. There is a verb version, though, of finding the antiderivative, that when you see it, you'll know what to do. And it's called the integral. So here is what the integral looks like. It looks like an elongated S, and you'll see in the next section why it looks like an S. It's because it stands for something that also begins with S. But it's an integral symbol, and it looks kind of like an F hole or an S hole on a fine instrument. The F hole usually has like a little flare right there, and it's kind of like an acoustical hole on an instrument. That's what it looks like. I typically write them like this. I don't really kind of accentuate them on the end, but that is the integral symbol. Then you're going to have a function following it. That is the thing that you're going to be taking the integral of, and then the dx at the end is the variable of integration. So what does it mean to take the integral of something? To take the integral of something means to find the antiderivative. So it turns out that we have another synonym here. The process of finding an integral is called integration. The process of finding an antiderivative is called antidifferentiation. Those two are the same. It means exactly the same thing. So if I ask you to integrate an expression, it means to find its antiderivative. If I tell you to solve a differential equation, you're going to do it by integrating both sides or antidifferentiating both sides. They're one and the same, okay? So that's our new symbol now. It's the verb. When you see the super S integral symbol, it means to find the antiderivative or the integral of what follows with respect to x. Just like when you saw this, it said take the derivative of what followed with respect to x. They're having fun next door, not unlike we are. In the next section, this is going to actually take on a little bit more meaning instead of just some syntax, okay? But right now, you're going to have an integral symbol on the left and the variable of integration, the dx, on the right. Those are like your two bookends. And then the function that you're going to be antidifferentiating falls in between them. Let's try out our new notation. Let me throw an extra bonus one here. The integral of x squared plus 2x with respect to x. Go ahead and evaluate that integral. Notice if your integrand, that's the thing that we take the integral of, if it's more than one term, you have to have it in parentheses, because as we saw in the differential, or the linearization and differential section, this dx is a singular unit, and without the parentheses there, it only looks like the 2x is being multiplied by it. All right, so of course this integral means to do what with the x squared plus 2x? Tickle it? We'll find the antiderivative. Okay, so it becomes 1/3 x cubed plus x squared plus c. Yeah. Now, while we're here, let me tell you a little bit more detail about this. This is actually called an indefinite integral. It certainly is an integral, but there are two types of integrals. You have a definite integral, which we'll see in the next section, and an indefinite integral. So indefinite integration is the same as antidifferentiation. And right now, you could just think of it as being an indefinite integral because our answer is an indefinite answer, right? It's a non-particular solution. We have the plus c there, so indefinite in this case kind of means general. We're not quite sure what it is. It's also a variable, and variables can take on anything, so it's indefinite in that respect. Okay, so let's look at some syntax then, how we're going to use this notation. Find the particular solution for the following differential equation. All right, is this a first order or a second order differential equation? It's a second order differential equation because our expression is equal to a second derivative. So to solve it means to get back to the original function, which is y equals. And we're going to have to do it in succession. So the first thing we do is find the antiderivative. All right, so let me show you that over. Let me show you what it looks like. You have d squared y, I'm just going to rewrite it here, equals 12x squared plus 6x minus 4. I don't want you to get hung up on the notation right now, but what we're going to be doing in a whole section to come soon is we're going to split this up into the following. dy dx, the integral with respect to y of the integral of 12x squared plus 6x minus 4 with respect to x. Okay, so it's kind of like when we take the derivative of both sides like we did with implicit differentiation. Remember, we first start off by saying d dx of this function equals d dx of this function. We took the derivative of both sides. Later then I showed you the shortcut was just to do this. It's the same thing with the integral. You can actually take the integral of both sides. But because each integral has a bookend, namely a dy or a dx, we're going to take the d squared y dx squared. We're going to keep the integrand as the first derivative, dy dx. We're going to keep one of the dy's on the left-hand side. And then the dx from the bottom, one of them, we multiply on the other side to get a dx bookend over there. So don't worry about the notation right now. I just wanted to introduce it to you. All right, so now on the left side, what would be the antiderivative of dy dx with respect to, that's not even correct. Let me not even do that for the second derivative. It gets a little more confusing for the second derivative. Let's just do this. Let's just take the antiderivative informally in our head on both sides. What would be then the antiderivative of the second derivative? dy dx. Yeah, I should have had another derivative in that integrand. So that's okay if you do it like that. And then 12x squared becomes 4x cubed. Good. Again, you can do it in your head. Start with the exponent. 2 plus 1 is 3. Divide by 3. 12/3 is 4. Plus 6x, when you find the antiderivative, becomes 3x squared. Minus 4 becomes 4x, and then plus c. Okay, so now we have two options. We're still not solved for the differential equation. I have an unknown c. If you can find c before you proceed to the next level, you should do so. If you don't have enough information to find it, though, you can go on to the next level right away. So let's look at what part A is. I'm just going to move this information over and put it in the middle, so it's kind of like a common area for A and B. Notice on part A, I have two initial conditions. One of them gives me an initial condition regarding the first derivative, and the second initial condition regards the initial function. So in this case, because I have a point that satisfies the first derivative, I'm going to be able to find c before I proceed. So bless you. Let's do that. When y prime of 1 equals 3, you get 3 equals, and then we'll plug a 1 into our derivative we just found. We get 4 plus 3 minus 4 plus c. And now you can simplify. Your 3's divide out or cancel out on both sides. Your 4's cancel out on both sides, and you get c equals 0. So now, particular to this side, we have the first derivative, dy dx, equaling 4x cubed plus 3x squared minus 4x plus 0, so just minus 4x. Now, here's what I was trying to show you with the second derivative. If I then separate the dy dx here by multiplying both sides by dx, this is what we'll be doing a lot in an entire section later on. So this is kind of putting the derivative in differential format. Remember doing that? The derivative in differential format. Now that I've got my y's and dy's on one side and my x's, dx's on the other side, now you can take the integral of both sides. Now you can take the integral of both sides. And really, the integrand on the left is really a 1. So what would you take the derivative of with respect to y to get 1? Y, right? dy is equal to 1. So that is how we go backwards on that side. So we get y equals. Now, you don't have to show that right now. So if you just want to go from dy dx to y when you go backwards, that's fine. Now, on the right side, we'll anti-differentiate again. And 4x cubed becomes x to the 4th. 3x squared becomes x to the 3rd. And 4x becomes 2x squared plus another c. And we can reuse c because the first c is already solved for. So we can use it again. And now we have information that satisfies that function given to us up here. Y of 0 is negative 6. So to show that I'm doing that, y of 0 equals negative 6. Plug it in, you get negative 6 equals 0 plus 0 minus 0 plus c. That was an easy one to use. So c equals negative 6. And so finally, here's the solution. You get y equals x to the 4th plus x cubed minus 2x squared minus 6. We solved the second order differential equation by finding the particular solution whose second derivative was the original and whose original point passed through 0, negative 6, and whose slope at 3 or at 1 was 3. All right, let's look at part B then. On part B, I'm starting with the same second order differential equation. So when I take the first antiderivative, I still have this right here. Do I have the option now of finding c for the first derivative on example B? No, I don't, because instead of having a point that satisfies the derivative and then the function, I have 2 points that satisfy the original function. So I can't find c. I don't have enough information. I still have 2 pieces of information, but I can't find c right now. So now we'll just go straight to the next antiderivative, and I'm not going to write the notation out. I'll just go straight from dy dx to y equals. All right, so 4x cubed. Take its antiderivative, same as before. It's x to the 4th. Then we get x cubed minus 2x squared. But now, what's the antiderivative of the constant c? Cx, right? Remember, any constant, you just add an x to it when you antidifferentiate it. Because its derivative, the derivative of cx is just c. Plus, now I can't use c again because those two c's could be different. So you either call it d, or another letter, or you could use subscripts. If you want to call this one c sub 1, then you'll have c sub 1 and c sub 2. They just have to be different because they're not necessarily the same. Now I have 2 unknowns. Well, I have 2 pieces of information. So let's go ahead and use this one first. If you have an x equals 0, probably want to use that one first. It's a little bit easier. So y of 0 equals 4. We get 4 equals 0 plus 0 minus 0 plus 0 plus d. So d is equal to 4. So we know now that y is equal to x to the 4th plus x cubed minus 2x squared plus cx plus 4. And now we'll use the other ordered pair at 1, 1. At 1, 1. You get 1 equals 1 plus 1 minus 2 plus c plus 4. And you end up with those canceling. You end up with negative 3 equals c. So your final solution is y equals x to the 4th plus x to the 3rd minus 2x squared minus 3x plus 4. So notice the 2 different particular solutions to the same second order differential equations. The second derivative of both of these functions is identical, but they are in fact very different functions. Okay? There you go. Kind of fun going backwards. Kind of puts all the old derivative rules that we got and get tired of using in a new perspective. All right, any questions on those? All right, so we said that right now we only have tools of a hammer and a pickaxe. And so sometimes we need to manipulate our integrand into something more recognizable, something that we can use our hammer and our pickaxe on. So let's jump to example 6. Now we're using the verb format. It says evaluate each of the following. When you see something like that, What is that telling you to do? Take the antiderivative of that function with respect to x, or you could say find the integral of that function with respect to x. And it is an indefinite integral because you're going to end up with another indefinite variable answer. Okay, so right now all we have is the power rule and recognizing something as a derivative of something else. Can you just look at that integrand and say, oh, that's the derivative of Fred? No, I can't either. That doesn't look like Fred to me, Fred's derivative. It's definitely not the derivative of sine. I know that because that's cosine, and that isn't cosine. So we have to manipulate it into something that we recognize. What to do, any ideas, any help from y'all? The what? Yeah, it's going to be really hard to do Hody high in reverse, though, right? But it is a quotient. Man, if there were an antiderivative rule, like Hody high for antiderivatives, we'd be on it right away. But there isn't. There isn't a rule for integration. What's that? Here's what I would recommend doing. First of all, if you have any constants, constant multiples that is, in your integrand, you're going to want to pull them to the front. So I got a 5 in the front of the integrand, and I could factor a 3 out from the denominator. And now I leave it as 1 minus x squared to the 1/2 power all over. What do I have in the bottom when I factor the 3 out? 1 minus x squared to the first, dx. The reason you want to do that is constant multiples, remember, they go along for the ride. 5/3 now is in the beginning of your problem. He is going to be in your final answer. And then if you generate any other coefficients, you can then combine them with the 5/3 at the end. So get your rider out front. Now it looks a little more promising. Again, I'm working straight down without equal signs. Now I have the bases are the same, so I can add the exponents. That's going to give me 1 minus x squared to the negative 1/2 power, right? To the negative 1/2 power means then that it's in the denominator under a radical. And now that I've written it to look like that by combining exponents, it's like, hello, derivative of Mr. what? Arc sine. Yeah. So now I recognize it. So 5/3 goes along for the ride, and the antiderivative of this is then arc or inverse sine of x, and then plus c because we are a champion. Manipulate it until it looks like something you recognize. All right, we're making good time here. I'll let you chew on this one. Nom, nom, nom. Notice the variable of integration here is t. That's not a big deal. There is no quotient rule for integration. Lucky for us. That would make it too boring. Yeah, good. I see y'all. If you have trig involved, it's probably going to involve the use of identities, right? Jason has it. Trial and error is really kind of the only way to go about doing it. But if it has trig in it, we're probably going to manipulate that into something that is a known trig derivative. So if you come back up here, we're trying to make it either look like a cosine, a sine, a secant squared, a cosecant squared, a secant tangent, or a cosecant cotangent. All right, so if you notice, then, if you bring the cosine to the top, you're going to be left with sine times secant squared. Secant squared is a known derivative, but not with a sign in front of it. So you're probably going to have to split it up. Call it sine of t over cosine of t times cosine of t. Because keeping it all together with cosine squared didn't really help. Now you can group or associate your factors like this. What's another name for 1 over cosine? Secant of t. What's another name for sine over cosine? Tangent of t. OMG. I have an integrand of secant tangent. I know that to be the derivative of what? Secant. So that is the antiderivative of secant tangent. And of course, because we're champions, plus c off to the side. So some of y'all I saw were doing Pythagorean identities. That's a fair game, right? 1 minus sine squared in the bottom. But ultimately, doing it this way leads you towards something you recognize. All right, probably the last one of the day. Tangent squared plus 4. I know how to find the antiderivative of 4 with respect to p. Is tangent squared a known derivative? No. What are the known derivatives? Not tangent squared, but secant squared is a known derivative. Gosh, if only there were a way to write tangent squared in terms of secant squared. Is there a way to write tangent squared in terms of secant squared? Yes, there is. Baby PID number 1. There it is. So let's go ahead and replace it. Tangent squared then, with respect to p, is the same as secant squared of p, what? Minus 1, plus the 4 that's there with respect to p. Now I'll simplify. We only want to take the antiderivative at the same time. Secant squared of p then plus 3 with respect to p. Now whenever you take the antiderivative, just like when you take the derivative, the dp goes away, and in this case so does the integral symbol. So what's the antiderivative of secant squared? Tangent. Plus, what's the antiderivative of 3 with respect to p? 3x, or in this case, 3p. And then we finish it off with a plus c. So if you ever see an integral of tangent squared or cotangent squared, remember cotangent squared is this, 1 plus cotangent squared of x equals cosecant squared. So because secant squared and cosecant squared are known derivatives, if you ever see a tangent squared or a cotangent squared as a term in your integrand, you're going to use the 2 baby PIDs to put them in terms of secant squared and cosecant squared, respectively. Okay? All right, I think we'll stop right there for today. We got about a minute left. So that was through example 6C. You should be chipping away at your worksheet. Hopefully you'll find it to be fun and worth your efforts.